Now we want to look at how a computer can remember a song. And so this, just like with the images, we're translating sound or music into numbers. So one thing to note before we get started here, theoretically, if you had a sensitive enough mic, you could perfectly translate. Perfect, that's just a mess, so let me restart that. We could perfectly translate sounds into electrical signals. So we already learned how a vibrating diaphragm can move a magnet, and that can create electrical signals. So if you did this perfectly, you could have, you could perfectly record the sound, and that means theoretically you can connect it to a speaker and perfectly replicate that sound. This type of signal is known as an analog signal. So if you ever get into high-end audio, stuff like that, or you get into sound engineering, you'll need to know the difference between analog and digital. Analog has no upper limit, generally speaking, on how detailed and exact it can get. But if we want to store that digitally, we can't, because a signal of electric signal is not a digital like storage of ones and zeros. And this is where we kind of glossed over it on the how does a computer hear. Now we're getting into how does it actually store that data or process it. So that analog signal is sampled at various points, and they basically see how strong is the signal every hundredth of a second. And then if they record all those numbers, you can create a pretty good graph of what you had before. And so this is known as the sample rate. And if you are curious or kind of want to know what that is, typically you see those sampling rates as ranging from 44.1 kilohertz all the way up to 96 kilohertz is kind of the standard for music and audio. So if you are ever looking at music or at recordings and stuff and you see this 44.1 kilohertz, that just means every second they're recording 44,000 points along that wave. If it was at 96, that means every second 96,000 measurements are being taken of the sound. So obviously the higher that number, the more precise you can kind of replicate the sound digitally. But also the more data you have to store and the larger the file size gets. So what do we mean, and what does this look like when we actually get into the recording of it? Well, imagine this is our sound wave. So this is what the sound was doing. So you had lots of high pressure zones at the peaks here, and then lots of low pressure zones at the valleys, right? So that's just like what we've talked about before. This can be replicated perfectly on an analog signal, but if I want to save it, if I want to record this digitally and save it for later, what I need to do is basically come along and take measurements for every chunk of time. So I might take a measurement here, then I'll take another measurement here, then I'll take another measurement here, take another measurement here, here, here. So these are just measurements at different fixed intervals of time. So like every second would be a really bad audio recording, but every second take a recording and you get a value. And then what the computer does when it wants to play it back, it just says for this period of time, it looks like that. For this period of time, it looks like that. For this period of time, it looks like that. And you can see that we kind of get a pretty good replication, a blocky replication, but a pretty good replication of our sound wave. And that's kind of what goes on with that. And you can see that if you had a faster sampling rate, like you took more samples, your blockiness would matter less, right? Because you get closer to the sound wave. And so this is what's happening, and this is why kind of if you find someone who's really snobby about their audio, they'll complain about digital audio because you lose the smoothness. Now, in reality, the computer knows that it should be smooth, and when we do fancy things with actually playing it back, they will attempt to guess and smooth things out. But one problem that you could have, because real audio signals will be much more jagged than this, if your sampling rate was too infrequent, say you just got this measurement like this, and then another measurement like that, you can see that you can lose peaks or lose behavior if your sampling rate is too infrequent. And so that's where people will complain about low sample rate music, is you can lose some of the kind of finer details in that audio as you go along. But that's the basic idea. You can kind of see how these are all numbers, and they just would be basically recording the amplitudes. So, you can imagine just the height of each of these bars, and then that just being a long list of numbers that tells you how to redraw this graph.